Swayam Prabha. Digital India. Educated India.
Hello students, welcome to lesson 15 of module 4. As you know, module 4 is on payment design. In this lesson we will be discussing about how to design concrete payments as per Indian Roads Congress guidelines. The specific instructional objectives of this lesson are: after this lesson it is expected that the student would understand the basic failure modes of concrete payments considered in the Indian Roads Congress method of designing concrete payments. You would also be familiar with the theory used for analysis of these concrete slabs and as a result used for design of concrete payments. You would also be familiar, rather he would be able to select appropriate traffic and material inputs required for designing concrete payments as per Indian Roads Congress guidelines, and the student would also be able to select suitable designs, that is he would be able to design concrete payments as per Indian Roads Congress guidelines. The IRC guidelines are in IRC 58 in its 2002 version. It is titled as Guidelines for the Design of Plain Jointed Rigid Payments for Highways. We know that there are different types of payments: concrete payments, jointed payments, they can be continuous payments also without any joints, you can have even pre-stressed concrete. So, various types of concrete payments can be there, but these guidelines cover plain cement concrete, not reinforced concrete or pre-stressed concrete, and jointed slabs. The scope of this guidelines is that they are applicable for roads having a daily traffic volume of more than 150 commercial vehicles per day. Obviously, these guidelines are not applicable for low volume village roads. We understand what a commercial vehicle is. We are referring to trucks and other commercial vehicles which carry commercial goods. Buses also can come into this category. So, if the traffic intensity per day is more than 150, so the guidelines, the design thicknesses that are given by these guidelines will be applicable only for that type of roads. Concrete payments fail in different modes. This being a bound material, cement concrete, obviously cracking is the main mode of failure. Cracks can occur in different regions, in different directions, different locations of the slab. This can occur because of various reasons: load related, temperature related, cracking that is brought about by variation in change in volume of either the slab or the other layers in the pavement system, base or subgrade or foundation. So, we can have different types of cracks developing in the concrete pavement because of various reasons, and they also occur in different regions of the slab. As you can see, there are corner slabs, there are transverse slabs, transverse cracks, also there are longitudinal cracks. Another main type of failure that is very common in concrete pavements, but very difficult to understand and model, is mud pumping in pavements. Mud pumping is a phenomena due to which if there is a fine grained material below the slab, as the wheel passes over this and the slab at this joint deflects, it pumps out the fines from below, especially when it is in a saturated condition. So, gradually with each application of load at the joint or near the corner, the slab deflects and then pumps out the fines. So, after some time, if we have a base which is of erodible material, then there is going to be a void forming here, loss of support to the slab, and then leading to cracking of the slab. This is a phenomenon that is known as, also known as erosion of base or popularly known as mud pumping. Erosion is a result of mud pumping. There can also be blow ups occurring in concrete pavement, especially when, because of increase in temperature, the slabs try to expand, and if there is no provision for the expansion of the slab, it may buckle up and it may lead to crushing of this portion at this joint. So, as we discussed in the previous lessons, there has to be sufficient provision made along the length of the slab to accommodate this increase in length of the slab because of increase in temperature. Now, let us say what are the failures that have been addressed in IRC 58 2002 version. Load induced cracking because of application of very heavy loads. Cracking can be because of two main reasons. A very heavy load is applied which induces tensile strength which is more than the strength of the concrete. That single load itself can lead to cracking of the slab. On the other hand, if you apply loads of lesser magnitude repeatedly, they also can produce cracking in the slab because of what is known as fatigue phenomenon. So, there are two types of damage that we are concerned about: damage caused by heavy loads, also fatigue damage caused by loads of lesser magnitude, but applied repeatedly. Obviously, for a highway pavement, there will be number of wheel loads that are going to be applied, vehicular loads that are going to be applied. These are going to be applied repeatedly, magnitudes are going to be different. It is not very common that we are going to be having a very heavy load which alone is going to produce damage to the entire pavement. It is usually the repeated application of these wheel loads that is going to be causing cumulative damage, which subsequently ultimately leads to the failure of the pavement. These are wheel load associated failures, either due to heavy load or due to repeated application of loads. The other type of cracking that can occur, this we have discussed in the analysis of concrete pavements, is the thermal cracking, either because of curling up or curling down of slabs because of variation in temperature within the slab, or also because of contraction and the restraint provided to contraction by foundation. So, the thermal stresses also can lead to cracking of the slab. For analysis, concrete pavement is modeled as a slab on Winkler foundation. We have discussed about Winkler foundation in the previous lessons. Winkler foundation can be modeled as a set of springs. So, this is a slab on a spring foundation. This is the model adopted by IRC 58 2002 for analysis of concrete pavements. The foundation is represented by its spring constant known as modulus of subgrade reaction K. The analysis of concrete pavements or the solution of these problems is based on Westergaard's analysis and Pickett and Ray's works. We just mentioned that modulus of subgrade reaction is the parameter used to describe the foundation for concrete slabs. So, the modulus of subgrade reaction, as we have discussed in earlier lessons, can be obtained by conducting a plate load test on the foundation. If it is already a foundation is laid or trial section of a foundation is laid, and plate load test can be conducted on that. Using that, we can plot load versus deflection diagram. So, the slope of this line curve at a specified deflection gives you the modulus of subgrade reaction. So, the load is gradually increased and the deflection of the foundation is observed. So, the ratio of pressure to the settlement corresponding to 1.25 millimeter deflection gives the modulus of subgrade reaction. What is to be noted is the test has to be conducted using 750 millimeter dia plate. Also, this test is typically has to be conducted when the pavement is when the foundation is in its worst condition, which would be naturally be soon after monsoon, when it is in a saturated condition, or in terms of the moisture condition, it is going to be in its worst condition. So, that is the condition we have to simulate, that is the worst condition that the pavement can have. So, we have to use a 750 millimeter dia plate. We also have to conduct the test corresponding to worst moisture condition. In case we are not able to conduct the test using a 750 millimeter dia plate, the other plate normally that we use is a smaller size plate, because with 750 millimeter dia we have to apply large magnitudes of loads, that may not be possible in all cases. So, we can go for a smaller plate, 300 millimeter dia plate. If the subgrade or foundation is of homogeneous nature, then approximately K value corresponding to 75 centimeters or 750 millimeter dia plate can be obtained using this correlation. K 75 is half the value that we obtain using a 30 centimeter dia plate. As I just mentioned, the ideal period for conducting this test is during or soon after the monsoon, where we expect the foundation to be in its weakest condition. To adjust the K value obtained at any other time, which is not its weakest condition, to correspond to its worst condition. So, from the K value that is obtained at any other time, to obtain the K value that could have been obtained in its worst condition, we can make some adjustments to the value that is obtained in a given season by conducting CBR tests on subgrade soil samples compacted at field density and field moisture content and tested before and after the saturation. So, we have to find out saturated or soaked CBR value. We also have to find out the CBR value on the specimen which has been prepared corresponding to the field density and then moisture content corresponding to the density, rather the moisture content which corresponds to the period in which we have conducted the plate load test. So, similar moisture will have to be used in preparing the specimen, CBR value have to be determined. Similarly, this specimen will have to be subjected to soaking for 4 days and that value has to be determined. So, the comparison of these two CBR values will give us an idea as to how much adjustment has to be made to the K value that has been obtained in a given season for a particular moisture content. But obtaining K value by conducting plate load test is not always feasible, may not always be required. So, many a time the K value is estimated from CBR value. This can be done using the table that is recommended by IRC 58. For example, for homogeneous soil subgrades, K value can be estimated using CBR value. This is not a linear relationship. So, K value expressed in terms of Kg per centimeter square per centimeter, because this is pressure per deflection. If the soaked CBR value is 4%, the corresponding K value can be obtained as 3.5. If the soaked CBR value is about 20, the corresponding K value is about 6.9. Of course, this is an approximate estimation in case we are not able to conduct the plate load test and obtain the K value. But most of the times, especially for highways, we do not normally place the slab directly on subgrade. So, we either have a granular subbase or granular base or a cement treated base. So, the cement treated base plus the subgrade forms the foundation. There is slab below that you may have 1 layer, 2 layer, 3 layers. All these layers that are there below the slab form the foundation. So, we have to have one equivalent parameter, that is K value, representing the strength of all 3 or 4 layers that you have below the slab. For example, if there is a granular or cement treated subbase over subgrade, the effective K value can be obtained if you know what is the K value of the subgrade, or that is, if you know the CBR value of the subgrade, we can estimate what is the K value of the subgrade, and the effective K value over untreated granular layer of subbase with different thicknesses. That means, over subgrade, if you place granular subbase of different thicknesses, say 15 centimeters. So, if a 15 centimeter thick untreated granular layer is of subbase is placed over a subgrade having 5.6 kg per centimeter square per centimeter K value, then the combined K value of both these layers, subgrade of 5.6 and 15 centimeter granular subbase, will be 6.3. Similarly, if a cement treated subbase is used on this same type of subgrade, 15 centimeter thick cement treated subgrade is used, then the combined K value will be 17.3. So, this is the value we are going to use in the analysis. Usually, a separation membrane of about 125 micron polythene sheet is provided between subbase and pavement. This is a condition that is recommended by Indian Roads Congress. Some agencies do not recommend this. The implication of this is, if this is the slab and below we have foundation, so we are placing a polythene sheet between this, making this ideally a smooth interface. The advantage of this is, when the slab tries to contract, especially we are concerned about contraction of the slab, because that is going to induce tensile stresses in the slab. When it tries to contract, the restraint offered by the foundation will be reduced because of the smooth interface. Thereby, the transverse cracking that comes because of contraction or shrinkage of the concrete will be reduced significantly. If one is very much concerned about this type of failure, this would be a good idea to provide a smooth interface between slab and the subbase. This interface, smooth interface, can be provided by a membrane of 125 micron thick plastic sheet. But by doing this, if there is a dry-lean concrete base placed over, nowadays a dry-lean concrete base is recommended to be placed over subgrade, over dry-lean concrete base concrete slab is placed. So, dry-lean concrete base or subbase also has significant strength. When the concrete slab is roughly bonded with dry-lean concrete base, it can mobilize more strength out of the DLC, and that can reduce the overall wheel load stresses. It depends upon which stresses we are considering to be more critical. We are trying to reduce wheel load stresses, it may be a good idea to make the interface to be a rough one by not providing this plastic sheet. But if we are concerned about shrinkage stresses, contraction stresses, then plastic sheet may be a better idea. Also, to facilitate quick disposal of water that is likely to enter the subgrade, drainage layer should be provided beneath pavement throughout the road width above subgrade. If there is a significant requirement of drainage, a drainage layer over subgrade can be provided. This slab concrete is typically represented in terms of its elastic modulus value, Poisson ratio value, and coefficient of thermal expansion. So, these values are to be determined experimentally for a given grade of concrete that is going to be used. The value of E, value of mu, and also the value of alpha are to be determined experimentally, but we can take the values recommended by IRC. These are the typical values only, as modulus value to be 3 into 10 to the power of 5 kg per centimeter square, Poisson ratio value as 0.15, coefficient of thermal expansion which of course varies with the type of aggregates used, but a typical value can be 10 into 10 to the power of minus 6 per degree. Another characteristic of concrete that has to be considered, and very important one that is its fatigue behavior. As we understand, when concrete, either beam or slab or any other structural member, when it is subjected to repeated application, repeated flexure, so the accumulated damage that is going to be caused by these individual wheel loads or individual load repetitions will subsequently ultimately lead to fracture or failure of the member. So, this is what is known as fatigue. Repeated application of flexural stresses by the traffic loads causes fatigue damage. We use a parameter known as stress ratio to identify the magnitude of load, individual load that is applied with reference to the failure load. Stress ratio is defined as flexural stress due to a given load, whether it is a beam or slab. When a given load is applied, we can calculate the tensile stress using a certain theory. That stress divided by the flexural strength of the concrete. Again, the same member, if you go on applying incremental load, it will fail at some point of time. So, using that load, if you calculate the tensile stress, so that is the flexural strength of the concrete. So, applied stress divided by the flexural strength is known as stress ratio. So, for a stress ratio of 0.45, that means the applied load is of such magnitude that the stress ratio would be less than 0.45, then it is expected that the concrete will be able to sustain infinite number of repetitions of that particular magnitude of load. So, if the same load or even lesser loads are applied repeatedly any number of times, it is believed that the member will not fail in fatigue mode. But if the stress ratio is more, that means the load applied is more than the magnitude that is sufficient to cause a stress ratio of 0.45, then there is going to be damage that is going to be accumulating. So, the number of repetitions concrete can sustain those load repetitions is given as a function of stress ratio. For stress ratio between 0.45 and 0.55, n number of load repetitions to failure is given as a function of stress ratio with this expression. If the stress ratio value is greater than 0.55 for heavier loads, it is given by a logarithmic relationship. Log n is equal to 0.9718 minus SR by 0.0828. So, this is the two segmental relationship. For different ranges of stress ratio, there are different relationships that are to be used to define the number of repetitions to failure for a given stress ratio. So, that means if we know how many number of repetitions are going to be applied on the pavement during its service life period, 10 years or 15 years or 20 years, it could be 50 million to 100 millions. If you know what would be the order of magnitude of loads of each one of those loads, and we can apply that load on the pavement, analyze the pavement and calculate what is the tensile stress, calculate the stress ratio. Using the stress ratio, if you know 5 to 6 tons loads, about 10,000 loads are going to be applied. So, what is the total damage caused by all these 10,000 loads of this magnitude can be computed using these expressions. The estimation of cumulative traffic during design period and heaviest load has to be made. This is how we consider the design traffic. We are interested in what is the total number of repetitions of commercial vehicles and what are the loads that are going to be carried by these loads and what will be the heaviest loads that are going to be applied. So, we have to have an assessment of the total traffic volume and also the heaviest loads. Assessment of traffic usually has to be based on a 7-day 24-hour count. Obviously, we have to make traffic projections for the future, next 25 years or 30 years of design period, but this has to be based on the traffic counts that we make in the present situation for a short time period. So, this has to be done for a 7-day continuous 24-hour period. For making projections, an average annual growth rate of commercial vehicles, we are only interested in commercial vehicles because these are the vehicles that are which carry more load, heavy loads, and then these are the vehicles that are going to be causing damage to the pavement. So, we are interested in only commercial vehicles. So, the average rate of growth of commercial vehicles is typically can be taken as 7.5%, but this has to be actually worked out on the basis of various exercises, but if it is not available, IRC recommends you can take a value of about 7.5%. The design period is normally considered as 30 years. It can be taken as 20 years when traffic intensity cannot be predicted accurately, because building concrete pavements is a very costly exercise with very high initial cost. So, if you are not very sure about the total volume of traffic that is going to be utilizing the facility over the next 20 years or 25 years or 30 years, because 30 years is the design period recommended by IRC 58 for concrete pavements. So, if you are not very sure about the traffic volumes that are going to be utilizing the facility over the next 30 years, then we can design the pavement for shorter duration, that is 20 years. Also for low volume roads, we design it for 20 years. The estimation of cumulative traffic can be made on the basis of initial traffic counts that we make, given as C is the cumulative number of axles during the design period. We are not dealing in terms of individual vehicles, we are in fact dealing in terms of individual axles. So, C is the cumulative number of axles during the design period. It is given in terms of A, initial number of axles per day in the year when the road is operational. It is not in the year, or it is not the number that we obtain when we actually conduct the traffic survey. That has to be converted or again projected to the year when the pavement is actually completed and then ready for operation. R is the annual rate of growth of commercial traffic expressed in decimals. N is the design period in years. Another important characteristic of traffic loading that has to be considered is the lateral placement of wheel loads on the slab. The IRC 58 recommendations are to consider 25% of total two-way commercial traffic for two-lane two-way roads. If you have two-lane road and there is going to be two-way operation on that, 25% of the total two-way traffic has to be considered for design, not the 100% total two-way volume. We will discuss why this has to be so. Similarly, for 4-lane and multi-lane roads, 25% of traffic in the predominant direction. If you have multi-lane roads in terms of either 4 lanes, 6 lanes or 8 lanes, so there is going to be one predominant direction, either in terms of the load that it carries or in terms of number of vehicles that travel in that particular direction. So, once we identify the predominant direction, we have to take 25% of the traffic traveling in the predominant direction. For new highway links where no traffic data is available, data from roads of similar classification and importance can be used. Obviously, when there is no road available, there is no traffic, current traffic, so you cannot conduct any traffic survey on any existing road. So, we have to take data from similar roads having similar importance and similar classification. The estimation of cumulative traffic is done for different axle load groups. We have to classify all the axle loads and find out in each axle load what is going to be the percentage of traffic or how many repetitions of traffic axles are going to be there during the design life period. This number is required. It is necessary to have data on axle load spectrum. We have to have some idea, we should be able to project what is going to be the axle load spectrum that is going to be utilized in the facility. 0 to 2 tons, how many axles, 2 to 4 tons, how many axles, what will be the load classification that we make for different axle load classifications, axle load groups, the corresponding frequency we should be able to project. It is expected that the weights and the number of vehicles in each direction are equal. Typically, this is how we assume. but we know that in many situations traffic in one direction carries heavier loads compared to the traffic coming from the other direction. If that be so, we can also take that into account in the design. We also need to have information on the heaviest loads, because we are also concerned about the damage caused by very heavy loads. We are of course concerned about the fatigue damage caused by repeated application of number of loads, but we are also concerned about the failure caused by one single application of very heavy load. So, a very heavy load is considered to be the 98th percentile load. That means, out of all the loads that we observed or all the loads that were projected to be using the facility in the future, only 2% of the loads will be heavier than the 98th percentile load. So, we are not going to be talking about the 100th percentile load, we will never have any idea about the 100th percentile load, but we consider the 98th percentile load, which may be exceeded about 2% of the time. So, this is the load for which we are going to check whether the pavement is going to be safe or not. The critical stress condition that is considered in IRC 58/2002 takes into account the factors considered for design of pavement thickness are, as we discussed earlier, flexural stresses due to traffic loads, temperature differential between top and bottom fibers, and resulting curling and resulting temperature stresses. So, these are the two stresses that are considered. These two factors are assumed to be additive under critical condition. Critical conditions would be during noon time, when both the curling stresses and wheel load stresses will be additive. The effect of moisture, if there is variation in moisture from top to bottom, that also can produce moisture gradient and then result in some stresses, but usually this is neglected because this will usually act opposite to that of the temperature changes, and hence it is ignored. The loads applied by single as well as tandem axles cause maximum flexural stresses when tire imprint touches the longitudinal edge. This is a critical position. So, when tire imprint when they touch the longitudinal edge, that is considered to be the critical position of the wheel loads. When tire imprints touch the transverse joints with or without dowel bar, part of the load is transferred to the other side of the slab by either aggregate interlock or by the dowel bar system that is in place. So, this causes lower flexural stresses both at the corner as well as along the transverse joints. We are trying to identify which is the critical region in the slab as far as the load placement is concerned. So, as we see here, if the loads are placed with tire imprints tangential to the longitudinal edge, that is considered to be critical. If you consider them tangential to the transverse edge, because of the continuity that we have across the other slab in terms of granular interlocking or in terms of dowel bar system if it is there. So, there is some amount of load that is transferred onto the next slab. So, the flexural stresses will be significantly reduced because the next slab is also participating in sharing this load, whereas along the longitudinal edge, this side of this you do not have any continuity. So, when the load is placed here, there is going to be heavier stresses compared to the situation where the load is placed across the transverse joint. However, if the slab is cast panel by panel with clear vertical joints, there is discontinuity along both the directions in the corner region. So, obviously that is the critical region. So, when you place a load there, corner flexural stresses will be the maximum, especially when there is no continuity, when there is no load transfer mechanism from between these two slabs, then the corner is going to be the critical region. What we just stated is depicted here. So, this is the case where the tire imprints are placed tangential to the longitudinal edge. This is the longitudinal edge, this is the direction of travel. So, the tire imprints are placed close to the tangential edge, this is the critical position. Similarly, this is a tandem axle with tire imprints placed tangential to the longitudinal pavement edge. Tandem axles carrying twice the load carried by a single load. For example, if you consider single load carrying 10 tons, and if you also consider tandem axle carrying 20 tons, which is double the load that is carried by a 10 ton load, tandem axles will cause nearly 20% lesser flexure stress due to the superposition of the negative bending moment of one wheel load over the positive bending moment of the other wheel loads. So, tandem axles can carry twice the magnitude of load that is caused by a single wheel load, but the resulting stresses that will be produced by tandem axle loads will be about 20% lesser than that produced by a single wheel load, single axle load. But however, tandem and tridem axles, these are multiple axle loads, may cause loss of subgrade due to higher deflection. These produce higher deflection, although the flexural stresses are much less than those produced by single axle loads, they produce higher deflection. If the number of such axles is significantly high, erosion failure has to be considered, because the slab is going to deflect significantly along the joints and near corners. So, this would lead to loss of subgrade support because of pumping. So, when you have a large percentage of these multi axle vehicles, so we have to be concerned about erosion failure. In India, still we do not have very significant percentage of multi axle vehicles. So, that is the reason why IRC 58 has not taken into account the erosion failure in its design considerations. We know that the legal axle load limits in India for single axle load is 10.2 tons, tandem axle is 19 tons, tridem axle is 24 tons. However, in actual practice, many of the vehicles carry much heavier loads on the axles, and this loading pattern has to be taken into account. We cannot believe that these are the legal axle limits, so we are going to design for these as heavy loads only, because we know that there is going to be much heavier loads that are going to be applied. We have to actually take that actual practical loading pattern into consideration and design accordingly. Obviously, for this we have to conduct an axle load survey. Minimum sample size of 10% of the total vehicles in both the directions will have to be sampled to get a proper axle load spectrum. Higher axle load induce very high stresses in the pavement and result in consumption of fatigue life of concrete. Contribution of different axle load groups towards fatigue damage must be determined. 90th percentile axle load, which is considered to be heavy load, should also be considered for damage caused due to application of a single heavy load. Other traffic related or load related considerations are tire pressure and shape of the contact area also govern the load stresses. Tire pressure will be in the range of about 0.7 to 1 MPa. So, 0.8 MPa is recommended for consideration in the design. Load safety factor is also used, which takes into account the unpredicted heavy axle loads. For expressways, this brings in an additional safety factor into the design. For expressways, national highways and other important roads where there will be uninterrupted traffic flow and high volume of truck traffic, we are going to use slightly higher safety factor, LSF of 1.2. Roads of lesser importance having low proportion of truck traffic, LSF of 1.1 will be used. For residential and other roads, no load safety factor, no additional safety, so that is LSF of 1.0 is used. For calculation of wheel load stresses, Indian Road Congress 58 2002 guidelines recommend use of IIT Rigid computer program developed at IIT Kharagpur for computation of wheel load stresses in the edge region. As identified already, edge region is considered to be the critical region as far as the wheel loads are concerned. So, this computer program gives wheel load stresses in the edge region because of application of single loads, tandem loads, single axle and tandem axle. This computer program is based on Westergaard's analysis and Pickett and Ray's analysis. Typical charts for those who do not use this program, typical charts for estimating edge stress due to wheel loads are also given as appendix in IRC 58. For a given axle load, for a given slab thickness and for a given foundation K value, edge stress due to axle load can be estimated using the chart. A typical chart looks like this. For a selected slab thickness and for selected K value, it can be combined K value. For a given axial load, the flexural stress due to this load in the edge region can be obtained directly from the charts. One can of course use the computer program, and for any intermediate load, for any intermediate K value, for any slab thickness, the flexural stress can be computed. This is the expression adopted in IRC 58 for computation of corner stress. This is the Westergaard's equation modified by Kelly. In this, it is given as stress in the corner region as a function of given as 3p by h square, where p is the wheel load, h is the thickness of the slab, into 1 minus a under root 2 by L. This is L, where a is the radius of load contact area, L is the radius of relative stiffness. This is the parameter that were discussed in the earlier lessons. IRC 58 also considers temperature stresses because of variation in temperature within the slab thickness. So, concrete pavements undergo daily cyclic variation of temperature differential within the slab. To top is usually hotter compared to bottom during the daytime. So, the slab tends to warp up during day or warp down during night time. These two situations are depicted here. If the top temperature is more than the bottom temperature, it is going to be taking the shape, its self weight or any other restraint that is available from the foundation is going to be pulling this down, resulting in tensile stress at the bottom and compressive stress at the top. On the other hand, if the top temperature is less than the bottom temperature, this is how it is going to take shape, and the self weight of the slab is going to pull this down and resulting in tension at top and then compression at the bottom. The restraint provided by self weight of the slab and foundation to warping causes warping stresses. Restraint offered by slab weight at any section is a function of the weight of the slab up to that section. So, corners will have very little warping stress unless dowel bars are provided. Restraint is maximum in the slab interior and somewhat less in the edge region. So, the restraint or curling stresses are going to be maximum in the interior. Next, they will be slightly lower in the edge region, they will be almost negligible in the corner region. Typical temperature differentials are recommended by IRC 58 because for a given region we have to assume some temperature differential, maximum temperature differential from top to bottom. So, these are recommended by IRC 58. These values can be seen from the guidelines. For example, for the region covering Bihar, Jharkhand, West Bengal, Assam and Eastern Odisha, excluding hilly and coastal regions, the recommended temperature differentials are for different thicknesses of slab, different temperature differentials are recommended. For example, for 20 centimeter thick slab in this region, the temperature differential to be assumed is 16.4 degrees centigrade. For computation of warping stresses, especially in the edge region, although we know interior region the warping stresses are going to be more, but since we are combining both the wheel load stresses and the warping stresses and considering this combination to be critical, so we are considering this combination to be critical in the edge region. So, that is why we are calculating wheel load stresses in the edge region and also the curling stresses or warping stresses in the edge region. So, the expression for computing warping stress in the edge region is given using Bradbury's coefficients as a function of modulus value of concrete, coefficient of thermal expansion of concrete, T is the temperature differential from top to bottom within the slab, and C is the Bradbury coefficient. Bradbury coefficient, as we have seen in the lesson on analysis of concrete pavements, can be obtained from the dimension of the slab and from the parameter radius of relative stiffness, where B is the free length or width of the slab. So, since we are considering the edge region, we will be considering the length of the slab in the longitudinal direction. So, from the dimension of the slab we can obtain the coefficient to be considered, and this can be substituted in the expression that was seen in the previous slide, and we can compute the edge stress. So, the critical combination of stresses for wheel load, corner stress will be more because of discontinuity in two directions. It will be more than edge stress, while edge stress is going to be more than the interior stress. Whereas warping stress, interior will be more than edge will be more than corner. Daytime interior and edge is the critical combination. Load and warping produce tensile stress at bottom. Nighttime load and warping stresses produce tensile stresses at top. The combination of stresses in the edge region is generally considered to be critical. So, it is necessary to also check for corner loads. Although we are concerned about the edge region, IRC recommends that we should also check for the corner load stresses. There will be different types of joints in the concrete pavement. Longitudinal joints in the pavements of width more than 4.5 meters to allow for transverse contraction and warping. Contraction joint spacing of about 4.5 meters for unreinforced slab thickness of 15 centimeters to 25 centimeters. For higher slab thicknesses, the spacing will be about 5 meters. Expansion joints are normally to be omitted if dowel bars are provided across contraction joints. The load transfer across joints is to be provided by dowel bar system across transverse joints. The design approach consists of the main inputs will be axial load spectrum. We have to have information on the axial load spectrum, the temperature differential, grade of concrete we are going to use, foundation strength, and the dimensions of the slab, which can be obtained after fixing the joint spacing. So, the slab is to be designed to sustain fatigue damage and also flexural damage due to the application of heavy loads. Erosion failure though is considered to be important if we have multi-axle vehicles which produce higher deflections, but it is not very common that we see many multi-axle vehicles at the present situation. IRC does not recommend any analysis for erosion, but however it recommends provision of paved shoulder up to 1.5 meter beyond the pavement to reduce erosion and pumping. The design steps are: we have to stipulate the design values for various parameters, decide the type and spacing of joint, we have to select a trial design thickness and then compute the repetitions of axial loads of different magnitudes during the design period, calculate the stresses in the edge region due to single load, single and tandem axial load, and determine the cumulative fatigue damage. If the cumulative fatigue damage CFD is more than 1, increase the thickness and repeat the above steps till we are satisfied that the cumulative fatigue damage is going to be less than 1. We have to go on increasing the thickness of the slab. Then compute the temperature stress at the edge region. If the temperature stress due to the highest wheel load is greater than the modulus of rupture, select higher thickness and repeat steps 1 to 6. Design pavement thickness on the basis of corner stress if no dowel bars are provided and if no load transfer through aggregate interlocking is assumed. Let us take up a design example. This is the example given in the appendix 2 of IRC 58/2002, same is reproduced here. We are trying to design a 2-lane 2-way highway. The total 2-way traffic at the end of the construction period is expected to be 3000 commercial vehicles per day. Rate of traffic increase is expected to be 0.075, that is 7.5%. The slab width, this being a 2-lane 2-way highway, so each lane there is a longitudinal joint in the middle, so width is 3.5. So this is how it is constructed. There is a longitudinal joint here and the transverse joints are placed at 4.5. Total width is 7 meters, so this is 3.5. So, the dimension of the slab is 3.5 by 4.5. So, spacing of contraction joint is 4.5. Modulus of rupture of concrete, that is the tensile strength of concrete, is 45 kg per centimeter square. These are all inputs that we need for design. K of subgrade plus DLC, there is a combined subgrade plus DLC combination is there. The combined value is taken as 8 kg per centimeter cube. Modulus value of concrete is 3 into 10 to the power of 5 kg per centimeter square. Poisson ratio value of concrete is 0.15. Tire pressure is taken as 8 kg per centimeter square. This is the axle load spectrum obtained from an axle load survey. Single axle loads, load groups 19 to 21, 17 to 19 and so on, 9 to 11, less than 9. So, for different axle load groups, the corresponding percentage of axle loads are given. Out of the 100% axles, 93% are single axles and remaining 7% are multi axles, basically tandem axle loads. So, the distribution of tandem axle loads are also given here. The present traffic in terms of commercial vehicles per day is 3000 vehicles, commercial vehicles. A design period of 20 years has been taken, growth rate is 0.075. So, using this, cumulative repetitions that are going to be there during 20 years is computed as 3000 into 365 into 1.075, that is 1 plus r to the power x, that is 20, minus 1 divided by r, that is 0.075. The total number of commercial vehicles that are projected to be using this facility in 20 years is 47 million commercial vehicles. Considering 25% of this for design, so 0.25 into this value is 11.854 millions. Since the front axles do not carry significant loads, we are only considering the rear axles. So, we are going to have rear axles to be considered in the design are about 11.854657. To solve this, we are considering the midpoint for each load group for single axle 20, 18, 16, 14, 12, 10 and so on. The expected repetitions in terms of the percentages we have worked out. Similarly, for tandem axle also, for different load groups, what is the expected number of repetitions is also indicated here. We have selected a trial thickness of 32 centimeters and we have considered load safety factor of 1.2. So, the axle load is given here, axle load multiplied by load safety factor of 1.2 is also given. The corresponding stress as read from the chart is given. The corresponding stress ratio, stress divided by modulus of rupture is given. So, for this, the expected repetitions as shown in the previous slide is given. The fatigue life is obtained using this stress ratio by substituting this in the fatigue equations that we have discussed earlier is given here. So, this is the total fatigue life consumed, because this is the life and this is the expected repetitions. So, this ratio multiplied by 100 gives you the directly this ratio gives you the fatigue life that is consumed. Similarly, the fatigue life consumed is worked out for all the other load groups. The fatigue life consumed is also worked out for tandem axle load groups. For loads less than 32 tandem axle loads, it is not worked out because 32 itself the fatigue life is coming out to be infinite. The cumulative fatigue life consumed is about 1.1706. Obviously, the thickness is inadequate. So, the exercise is repeated with another trial thickness of 33. So, we can see that the cumulative fatigue life consumed here is 0.47, which is acceptable. So, the slab is now safe from fatigue considerations. The slab is now checked for warping stress also calculated using the stress for a length of 450 centimeters and width of 350 centimeters. The Bradbury coefficient from the figure is 0.55 and the corresponding temperature stress is 17.3 for a temperature differential of 21. So, the temperature stress plus maximum load stress 24.1 plus 17.3 works out to be 41.4, which is less than 45 kg per centimeter square. Hence, this thickness is okay from this consideration also. This slab is again checked for corner stress considering the heaviest load, that is the 90th percentile load, which is considered to be 16 tons, dual wheel load is 8 tons. So, the corresponding corner stress works out to be 15.52, which again is much less than 45, hence it is safe. To summarize, in this lesson we have discussed about the IRC method of designing concrete pavements. We also discussed about the performance criteria adopted for design in these guidelines. We also talked about the theory used to model concrete pavements and the equations or the models used for analyzing the load and temperature stresses in concrete slabs as per IRC 58/2002. We also discussed about the significance of different types of joints in concrete pavements. We have done this very briefly. We also discussed as to how to design concrete pavements taking into considerations fatigue phenomena, maximum wheel load stresses and temperature stresses. These are some questions from this lesson. Answers to this will be provided in the next lesson. How to estimate the modulus of subgrade reaction of a concrete pavement? Why is the separation membrane provided between the slab and subbase? What is the critical position of load considered for design of concrete pavement as per IRC 58? What is the need for using load safety factor in the design of concrete pavements as per IRC 58/2002? Now, let us discuss the answers for the questions that we asked in lesson 4.14, which was on design of flexible pavements as per ASTO design guidelines. What does ASTO stand for? ASTO stands for American Association of State Highway and Transport Officials. How is performance measured as per ASTO procedure? As per the ASTO guidelines, performance is measured or represented in terms of present serviceability index. In fact, the performance is to be represented in terms of a parameter known as present serviceability rating, which is to be given by a panel of experts. This rating has to reflect the comfort that is perceived by the road users while traveling on a particular road. By correlating the physical features of the pavement to the present serviceability rating given by the panelist, a index termed as present serviceability index has been developed. This can be estimated as a function of various physical features of the road, such as slope variance, which indicates the longitudinal variation in the profile, and roughness, for especially for flexible pavements, slope variance, cracking, patching and rut depth. What are the main parameters considered in the estimation of pavement performance as per ASTO design? This is a question which refers to the ASTO performance equation, which correlates the number of repetitions of standard axles, that is W18, that the pavement can serve satisfactorily. So, the parameters that are considered significantly are resident modulus value of the subgrade, loss in serviceability delta PSI, reliability factors and terminal serviceability index. These are the important parameters selected. What is structural number? How is it estimated? Structural number is an index that gives combined strength of the pavement. If you have 4 layers, so Sn is given as A1 D1 plus A2 M2 D2 plus A3 M3 D3, where D1 D2 D3 are the thickness of the top 3 layers, A1 A2 A3 are the layer coefficients, M2 M3 are the drainage coefficients. So, structural number gives us an indication of the strength of the pavement. Thank you.